Good afternoon, everyone. My name is Khengdauliu Chawang, and the title of this presentation is Characterization of pH Sensors based on Iridium Oxide and Gold Encapsulated Polypropylene Membranes. My presentation today has 6 sections. First is motivation. Second, limitations of paper-based pH sensors. Third, materials and methods. Fourth, results and discussion. Fifth, conclusion. And the final slide 6 is for acknowledgements. The motivation of this work comes from the need of pH sensing in diverse fields. Nowadays, paper-based pH sensors are intensively studied because they are disposable and low cost. A popular type of paper-based sensor is optical sensor, but its application is also limited to only aqueous solutions. pH sensing is needed in viscous, semi-solid, and other liquid with different colors. Optical pH sensors use color indicators to indicate pH levels that can compromise the pH resolution. For example, change in solution color can produce discrepancies in output pH. Another popular type of paper-based sensor is electrical pH sensor, which is the highlight of today's presentation. They can be used in wide applications such as aqueous, non-aqueous, and viscous. A paper-based electrical sensor is disposable, and its greatest advantage is low power consumption with small size features that can be used to connect to portable reader. Some of the current limitations for paper-based electrical pH sensors are high temperature and permeability. Most metal layer deposition techniques require high temperature, such as E-beam. Iridium oxide has been deposited by techniques like sputtering, but requires plasma uniformity and vacuum system. Processes like sol gel needs high temperature for iridium oxide oxidation, which paper-based devices cannot tolerate. Permeability is another concern, which is usually overlooked. It is required for medical application where airflow is necessary, such as smart bandages. Here in materials and methods, the schematic of electrode preparation is demonstrated. First, on polypropylene micromembrane, abbreviated as PPMM, by electroless method, gold is deposited, and the electrode is named PPMM add gold. Next, by electrophoresis and electroflocculation method, iridium oxide is deposited. The electrode is now named PPMM add gold add iridium oxide. The SEM image of the electrode surface is also shown. These SEM images show how gold and iridium oxide is deposited on each PPMM fiber. The first SEM image shows smooth PPMM fiber. Second image shows gold on PPMM fiber. And the third image shows how iridium oxide is deposited on top of gold. The electrode is biocompatible and has chemical inertness. Among other metal oxides, iridium oxide is known for its biocompatibility, super-Nernstian sensitivity, and wide pH sensing range. It can be used as multifunctional bioelectrode for wearable and implantable devices. The fabrication process also did not require high temperature. Gold was deposited at 30 degrees Celsius and iridium oxide at room temperature. The average pore size of the electrode is 0.247 microns, which can be used to filter out cells in blood or interstitial fluids. The electrode also has impressive charge storage capacity of 54.6 millicoulomb per centimeter square. For pH sensing characterization, multiple parameters were studied, which were also previously studied for Kapton-based pH sensors. First is sensitivity. We use the Nernstian equation to determine the redox potential. Second, hysteresis, which is defined as the standard error between settled potential at the same pH level. Response time is defined as time taken to reach 90% of the settled potential. Stability is intensively studied using 3 parameters, namely potential drift, potential fluctuation, and potential deviation. First, we define potential drift. It is the difference between the peak and settled potential. Second, potential fluctuation. The worst potential fluctuation is maximum change in settled output potential. Potential deviation, it is the potential difference between different test cycles tested in the same solution. Test 1 in our case means it follows the sequence of pH 2, 4, 7, 10, 13, 10, 7, 4 to pH 2. The potential difference between the working electrode and reference electrode is recorded using a LabVIEW-based program with a sampling rate of 7 samples per second. Sensitivity is investigated for 2 test sequences, acid to alkaline, which follows the path pH 2, 4, 7, 10 to 13, and acid to alkaline, which follows the path pH 13, 10, 7, 4 to pH 2. We observed super-Nernstian sensitivity of 62 millivolt per pH for acid to alkaline path and 61.6 millivolt per pH for alkaline to acid path. The super-Nernstian responses for both the cases show good quality of iridium oxide deposited. Ideally, Nernstian response is 59.16 millivolt per pH, but sensitivity can also be affected by oxidation states of iridium or ion exchanges mechanism on electrode surface as described by the equation, and thus produce super-Nernstian sensitivity. The plot here shows test sequence from pH 2, 4, 7, 10, 13, 10, 7, 4 to pH 2, and this is done to find the hysteresis. The sensitivity slope still shows a super-Nernstian sensitivity of 62 millivolt per pH. Hysteresis at pH 2 is 2 millivolt, at pH 4 is 6 millivolt, at pH 7 is 22 millivolt, at pH 10 is 10 millivolt, and at pH 13 is 7 millivolt. The lowest hysteresis at pH 2 is because of faster ionic exchanges of protons, and higher hysteresis at pH 10 is likely due to the presence of equal number of protons and hydroxyl groups in the buffer solution, which counteract ion exchanges on the electrode surface. To study the response time, we perform 2 types of tests. First is when electrode is immersed in buffer from its dry condition. The response time at pH 2 is 4.4 seconds, at pH 4 is 2.7 seconds, at pH 7 is 3 seconds, at pH 10 is 2.5 seconds, pH 13 is 1.6 seconds. The second type is when electrode is switched between 2 extreme pH levels. The response time when switched from pH 2 to pH 13 is 3 seconds, and when switched from pH 13 to pH 2 is 4 seconds. In all the cases, response time is less than 4.5 seconds. Now, potential drift. It is likely caused by ionic diffusion at the liquid junction potential of the electrode. In a timeline of 20 seconds, drift is investigated. Drift at pH 2 is 46.5 millivolt, at pH 4 is 35.2 millivolt, at pH 7 is 19 millivolt, at pH 10 is 20.4 millivolt, at pH 13 is 41.4 millivolt. The high drift is likely caused due to short noises, which arose in the first few seconds, but the potential quickly settled in less than 4.5 seconds at all the pH levels. Next, potential fluctuation is caused by hydrodynamics in the solution. It is extracted from drift study, which is the zoom-in time period for 2 seconds. Fluctuation at pH 2 is 3.9 millivolt, at pH 4 is 1.6 millivolt, at pH 7 is 0.26 millivolt, at pH 10 is 0.3 millivolt, and at pH 13 is 1 millivolt. Next is potential deviation. To study the potential deviation, we consider 2 cycles. Cycle 1 means tested in the sequence of pH 2, 4, 7, 10, 13, 10, 7, 4 to pH 2. Cycle 2 is a continuous test sequence from cycle 1. The plot shows worst potential deviation, which is at pH 13. The potential deviation similarly at pH 2 is 0.63 millivolt, at pH 4 is 0.81 millivolt, at pH 7 is 5.9 millivolt, at pH 10 is 16.3 millivolt, and at pH 13 is 20.6 millivolt. Using calibration curves at pH 2, 4, 7, 10, and 13. The corresponding pH deviations are 0.01 at pH 2, 0.01 again at pH 4, 0.09 at pH 7, 0.26 at pH 10, and 0.33 at pH 13. Now, in the conclusion, the fabrication process did not require any high temperature treatment. The pH sensing performance also exhibited a super-Nernstian sensitivity with impressive stability in less than 4.5 seconds. The small size and biocompatible properties of the electrode make it possible for paper-based microfluidic devices for biomedical applications. The electrical features also make it possible to integrate with other electronics to be used as a wearable element. We sincerely appreciate the support from Mary and Richard Templeton Endowment and also financial support from Ministry of Science and Technology of Taiwan. Thank you everyone for watching my presentation.